Hey everyone, in this video we're going to cover section 9.3. We're still going to be continuing our discussion of hypothesis testing with two groups, but now we're going to look at when the when the samples are two dependent samples, and so we're going to do the match pairs exercises. And so the example that I have today is the example 1 here, distracted driving. And so hopefully you have already read this from I posted the notes earlier, but essentially researchers at the University of Utah asked student volunteers to use a driving simulator to test whether distracted driving, so if you're talking on the cell phone, does that delay the reaction time? So versus if you're just listening to music or listen to an audiobook without the having a conversation distraction. So students were given a warm-up period to familiarize themselves with the driving simulator, and then the researchers had each student use the driving simulation machine while talking on a cell phone about something, and then again do the driving simulation while just listening to music or listening to an audiobook. So that will be the control group. So the reason that this is a match pairs and dependent samples is because we're using the same group of students. The same subjects are being in the treatment group and in the control group. It's just that the first time they might do the control group, right, just use the driving simulator while listening to music, and then they'll do it again while they're talking on a cell phone. And others might do it backwards. They'll talk on the cell phone first while using the driving simulation, and then do the control group, just listening to music while doing the driving simulation. So that's the idea, is that it's the same person doing both the control and the treatment group. So the students were randomly assigned as to whether they used the cell phone or the control setting for the first trial. And then we had 16 students take the survey or do the simulation. So what is the research question in this problem? So we essentially want to know, does talking on a cell phone delay your reaction while driving? So let's put that in here. So the cell phone use delay the driver's reaction time while driving. So if something was to happen, does it delay your reaction when you're talking on a cell phone versus if you're not? And so I think I skipped the part that it says, so at regular intervals, a target will flash red or green, and participants were instructed to press the brake button as soon as they detected the light. The red light. And so that's how the problem was set up. So we want to know, the cell phone use delay the driver's reaction time while driving? And then, is this an observational study or is this a randomized experiment? And how can you tell? So this is back to chapter 1. How do we know? Are we observing or do we have an experiment? Remember, experiment is when you have a treatment and a control group. And in this case, we do have a treatment and a control group. So this will be an experiment. Describe how randomization was used in this study. I asked the question, but I answered it in here anyway. The study presented here is an example of match pairs design. And I kind of already discussed why it's match pairs, but essentially each student in the study experienced both the treatment and the control, right? Driving while conversing on a cell phone and driving with background music or an audiobook. So randomization was used in the study, but only to randomly determine which treatment each student experienced first, whether they were in the cell phone, talking on a cell phone first, and then control later, the listen to music, or vice versa. So the match pairs design is preferable to a completely randomized design because the pairing helps control for natural differences in reaction times across the subjects, right? If a subject performs differently on the two treatments, we feel much more comfortable attributing that difference to the treatment than if we compare two different people, right? If I took you and somebody else, your friend, and said, okay, let's see the reaction times, it could be that you just react differently, right? You're two different people, versus if I just take you and do both, I can really tell, okay, like it's really the conversing on the cell phone that's affecting the reaction time. So match pairs, so applying the control group and the treatment group to the same subject sometimes is better. And this is the same with like when you're testing a drug, like people in pharmaceuticals or testing a treatment, right? If we want to see if an exercise routine is good in lowering cholesterol, we will test the same person. So we will do a cholesterol test before they start the exercise routine, and then measure their cholesterol levels again after they complete the exercise routine. And then we can see, because that will be better because it's the same subject. So that's how match pairs works, and this was randomized in the sense that each subject was randomized into which they did first, the treatment or the control. What are the observational units in this study, and what makes sense to use as the response variable? The observational units will be the 16 students doing the driving simulator. And the variable that makes sense to use here will be reaction times. But really, what we want to look at is the difference in reaction time. So here we will consider the response variable for the study to be the difference in reaction time, because we want to see what is happening since we're using the same subject, right, the same student, then we want to look at the difference in the reaction time when they did the cell phone, so the treatment group minus the control. So what was the difference in the reaction time? And then for each student, if it is actually the case that cell phone use delays the reaction time, what should we see in these differences? So that means that if cell phone use delays the reaction time, which time is larger, the cell phone time or the control? The cell phone, right? So we should see that this difference then will be positive. So now we're going to express the null and the alternative hypotheses to be tested here. So we want to use words and symbols. So our hypotheses, we want to test, the claim is that cell phone use delays the reaction time. So we want to see that this difference is then positive, greater than 0. So that was going to be our alternative hypothesis. And so our null hypothesis is going to be that there's no difference. So the difference will be 0. So let me write that out. But before I do that, we need to talk about the variables that we're going to use, because we're considering the variable, the difference in reaction times. So I'm not going to be doing 2 samples. I'm already going to be taking the difference, and so I will have just 1 value. So let me skip ahead a little bit to the notation. So here I did the t-test for the difference between means and dependent samples. So what we do is, for a paired t-test interval, a null hypothesis is usually going to be that the null hypothesis is this mu sub d is equal to 0, where mu sub d represents the population mean of the differences. So I'm not considering like as if I had 2 samples, because I'm looking at the difference between the treatment and the control, right? I'm looking at since the subject is the same, so then I look at one subject and then I look at the result in the treatment, the result in the control, subtract them, and then that is my variable. So I really just have 1 variable, the difference. And so this is a little different than what we did before when we had 2 proportions and 2 means, right? We were doing mu1 minus mu2 or p1 minus p2 because we had 2 different independent samples. Here, because we have dependent samples, we look at the difference already because those 2 values that we're getting are for the same subject. I hope that makes sense. It's a little confusing. So our test statistic then is d bar, and I can't explain what this is. So d bar is the sample mean differences. So what's happening then is, going back to the data, right, I can say, so I'm going to look, my variable is going to be the difference between the 2. So I'm going to do for subject A, the first student, 636 minus 604. And then that difference is my data value. Then 623 minus 556. that difference is my next data value. 615 minus 540, 672 minus 522, and so on. So I can create a new table of the differences, and now I'm doing my hypothesis test and everything on that new column of just the differences. So it's kind of like I'm taking this, that what looks like two samples, but I take the difference, and now I'm really doing a hypothesis test of just one sample. So that's kind of what's going on here. So when I express the null and alternate hypotheses, we're going to say then the null hypothesis is that there's no difference in reaction times for people driving while in a cell phone. So we're going to say the mu sub d, right? The difference, the mean of the differences is 0. So going back to when I was looking at the data, right? If I take the difference of all of these, I'm going to have a new column of all the differences. So what is the average difference? So that's what this is. So the average difference, we're saying is there's no difference, so it will be 0. And the claim is that no, when you're talking on a cell phone, that delays your reaction time, so meaning your reaction time will be longer. And so we can say then the mean of the differences will be greater than 0, positive. And this, remember, the alternative hypothesis tells you what kind of test you have, so this is going to be a right-tailed test. And just to review, the null hypothesis always has an equality sign versus the alternative hypothesis has something that does not involve an equal. So it's always less than, greater than, or not equal to. Whereas the null will have the equals, greater than or equal to, or less than or equal to. But most often than not, it's just the equals 0. So the data for this problem is preloaded in the StatCrunch group under the name Distracted Driving. So you can go ahead, pause the video, go to StatCrunch, log on to StatCrunch, and go to our group for this class and find the data, Distracted Driving. And then we're gonna do this. So what this instructions, sorry for my scrolling, I hope I'm not giving you a headache. These instructions, what they're going to do is essentially take our data and construct that column that I was talking about. So we're going to construct a column of the differences. We could do this one by hand because we only have 16 data values. So I could just do, right, start with the first one, 636 minus 604, and go down the line until I get to 554 minus 467 and figure out what those differences are. But what if I had 50 data values? What if I had 174 data values? We don't want to do it by hand, so we're going to use StatCrunch to help us. And so we're going to follow these instructions. So we're going to try to find our sample mean difference and then the standard deviation of those differences. So let me go ahead and stop here so we can have the instructions available. And let me pull up StatCrunch as well. All right, bear with me. I'm going to try to see if I can keep the two screens on the same, on the screen, or the two tabs on the screen. So let's pull up our data. So once you're logged on to StatCrunch, go to My StatCrunch, go to My Groups, and pull up our group. And then let's find Distracted Driving. Usually it puts it way at the end. I wish it put it at the beginning, right? Because that would make sense. That's the one we're using, but it puts it at the end. So let's pull up Distracted Driving. So here is our data, and we do have 16 data values. All right, so we're going to follow the instructions that are up here. So we're going to go to, we want to calculate the differences. So under the data tab, click compute expression, and we're going to double click on build. So I'm going to go to the data tab, which is right there, and click compute and then expression. And so this little window should pop up and we're going to build. So double click on build and then this window pops up. And so then we're going to go to the next set of instructions. In the expression box, double click the columns to create the expression we want to, essentially what we're doing is we're telling StackRanch to compute, to subtract the two columns, the cell phone column minus the control column, and then put the results in a new column. So that's what we are doing. So I need this screen to be bigger. So we're going to go to our column. So we want to go to cell phone. So double click on that and then go minus and then double click on control. And so you should have up here cell phone minus control. So that's what you want to create. So again, let me cancel this. Let me go over the steps again. So in case you missed it, but I guess you can pause and rewind. But let's go to build. And then we want to up here, notice that there's this little red little box. There we want to be able to say cell phone minus control. So cell phone, double click, and then click minus, and then control. Right, essentially now we're telling StackRanch to help us subtract those two columns. Hit OK, and then hit compute. And notice that it created another column. It says new column, cell phone minus control has been created. And so here is our new column. And now if because now it's a little confusing because I see cell phone there and cell phone there. So you can click on that and just change the name. So you can say cell phone minus control. And you can, I guess it doesn't really change it that much. Maybe we can make it bigger. We want to be able to see the name. And then now we do our standard summary stats. Right? We want to be able to find here. Now we're going to use StackRanch to explore the differences. So we want to find the mean in the new column and the standard deviation. So we're going to go into StackRanch and we're going to go to stat, summary stats, columns, and now we want cell phone minus control. And we want to find the mean and the standard deviation. So control, standard deviation, so it's that, and compute. And so these are my summary statistics for the differences. So notice that there are 1, 2, 3 negatives. So that means that these 3 students, so student I, student J, and student M, they actually had a delayed reaction time while they were in their control group. So while they were just listening to music or an audiobook, they had a slower reaction time than when they were talking on a cell phone. But that was only 3 out of 16. So all right, so our mean is 47.125 and our standard deviation 51.331. So I'll take those values and put them back in the notes. All right, back in our notes, we put our mean of the differences and the standard deviation of the differences. Do the data suggest that using a cell phone while driving may affect reaction times? Explain your answer and be prepared to show your work. Well, how do you show your work? Well, let's go back to StackRanch. We can even see here, as we discussed earlier, well, most of the students had, because the differences are positive, most of the students had a delayed reaction time, right? Longer reaction times while they were talking on a cell phone than when they were just listening to music. So yeah, the data suggests that there is a delay in response while you're talking on a cell phone and driving. So we can say the mean differences are positive, suggesting direction times while using the cell phone are larger. And to show your work, point to the data in StackRanch. So now that we have, right, there is, our mean difference is positive, so we have something to go for. So if you were creating your own study, which I will post your assignment to create your own study later this week, that if your claim is that there is a delay, but then the difference here, the average was that there isn't, if this difference was really close to zero or even negative, then you really wouldn't have anything to go for. You wouldn't continue the study because it's like, oh, my data doesn't support my claim. So you wouldn't continue to go do anything else, right? You wouldn't go do a hypothesis test or a confidence interval because the data collected from your sample doesn't support the claim that you're making. So you either have to then adjust the claim, or, was the data collected correctly, or modify whatever it is that you were trying to do. But essentially your sample data, you have to have something to say like, oh, my sample data supports my claim, so now I'm going to continue with the study and verify and do like a test of significance or a confidence interval. But if your sample data didn't support the claim, you wouldn't go on. Hopefully that makes sense. All right, so to do a hypothesis test, we need our test statistic. It also needs to satisfy the conditions of the central limit theorem, which the validity conditions are our samples have to be random or from a population that is normally distributed, and we have to have, oh, this is the part, normally distributed population, or our sample sizes are more than 30. In this case, we had 16, but it is from a population that is normally distributed, so we can say it satisfies the conditions, and so we can go on and find a test statistic. For the test statistic, we need those values that we just found. We need our d bar, which is the mean of the differences, and we need the standard deviation of the differences. So our test statistic is a t statistic because we don't know anything about the population standard deviation. So it's going to be our sample statistic minus our hypothesized parameter, mu sub d, which usually is just 0 anyway. So oftentimes you won't even see it in the formula. You might just see d bar over the standard deviation and over the square root of n. Sorry, I feel like I have to cough. That's why I may sound different. So that's our test statistic. And then once we find the test statistic, we can either do the critical region, right? Sketch the critical region and see if our test statistic falls in the critical region. We can do the p-value, or we can do the confidence interval. So we're going to calculate by hand the t-statistic. Then you stack crunch to determine the p-value of the t-test and make a conclusion. So let's go ahead and calculate by hand the t-statistic. So I'm just going to copy this and put it over there. So here's our formula. So we know from above, where was it, that our mean is 47.125 and the standard deviation is 51.33. So we're going to go back over here and put our mean 47.125 minus, that's our sample mean, minus the hypothesized mean. Our null hypothesis is that the differences is 0, so we're going to put 0 over the standard deviation of our sample of the differences, so 51.33 over the square root of n. And our sample size was 16, so the square root of 16 is 4. And then put that on our calculator, and we're going to get 5.68. So from here we can, just by looking at that, even just using the empirical rule, remember the empirical rule is if you have, if your standardized, if your z-score or t-score is larger than 2 standard deviations, right, then it is considered highly significant, so highly unlikely to happen. So this 5.68 is more than 2, more than 3.5. Sometimes 3.5 is like the benchmark of that is like way unlikely, so this is way past that. But if we sketch the critical region, so just coming here to my notebook, and if we sketch the bell curve, we will see, we said that this was a right tail test, right? We remember the alternative hypothesis was that the mean of the differences was greater than 0. And so that means And what was our, did we have a level of confidence, a level of significance? Determine p-value to make a conclusion. I should have said at some point, probably the 0.05 level of significance, if I didn't say that. This says 95% confidence level, so let's use a 0.05 level of significance to find our p-value. So I'm going back to the critical region here. So that means that if I'm looking at level of significance of 0.05, that means that since this is a right tail test, that means that 0.05 of the area is going to be over here. Now we can look at our t-table to see what the critical t is. What is our t-score that gives us 0.05? So let's go to the t-table. So coming over here to the t-table, and we had 16 students, so the degrees of freedom will be 15. And so we're going to go to degrees of freedom 15, and we want 0.05. So it's the 1, 2, 3, the fourth column. So 15 and 0.05. So 1.753 is my critical t value. So 1.753. Let's remember that. So here this is 1.753. So this is the t value. So this is our critical t value for a level significance of 0.05 with degrees of freedom equal to 15. Now notice that our t-score is 5.68. So when we're doing the critical region method, this is the highlighted part here. This is the critical region. Sometimes I call it the rejection region. I started to combine my words there. So this is the critical region, which I also call the rejection region. That means that you reject the null hypothesis if you're in this region. So 5.68 is definitely in here. So 5.68 is larger than 1.573. So based on this, we can reject the null hypothesis. And the null hypothesis was that the mean difference was 0, that there's no difference. So this is no. We reject that there's no difference. And so rejecting the null means we accept the alternative. The alternative is the claim that distracted driving delays the response, the reaction times. So that is using the critical region. Now to find the p-value, we run into this same issue that with the t-table we can't find that area, right? For degrees of freedom 15, we just don't have the p-value that we need, so we can't find it. So we have to use StatCrunch. So let's go back to StatCrunch and find the p-value there. And so what we're gonna do is we're gonna go to stat and do a t-stat for one sample with summary. And we're going to put in why one sample, because we did reduce the cell phone group and the control group to just be one sample. So the mean is 47.125. The standard deviation is the 51.33, and the sample size was 16. And so we can do a hypothesis test. It was a right tail test with the critical value of 0.05, so that's okay. And then we hit compute, and here is our data. So 3.67. Let's see. So seeing the answer in StatCrunch made me double check my math here, and I don't know where I got the 5 from. When you put this in the calculator, that should be a 3.68. But does that still work? Yes, it's still 3.68 is still larger than 1.753. So this is why sometimes I'm doing this by hand, and I must have input something wrong in my calculator, and that gave me a 5.68. Interesting thing is that the 68 was still correct. Um, but double checking with technology, right? I saw my T-score, and that's what made me be like, wait a minute, they're different. They shouldn't be different. So here I'm looking at my T statistic, my T standardized statistic, 3.67 to 3. So it's slightly off. So, but notice the p-value. Now I'm able to find the p-value, 0.0011. So that is our p-value. So going back to our notes here, we can say the p-value was 0.0011. Therefore, how do we make a decision? We compare the p-value versus the alpha, and our alpha is 0.05, so we are essentially comparing 0.0011 to 0.05, and which one is smaller, or p-value is smaller, which is, what does that mean? If the p-value is smaller, that's the area for 3.68. So which makes sense because 3.68 is over here, so this area is smaller. So it's contained within the rejection region still. So we can say because this is smaller, we reject the null hypothesis. So we get the same conclusion. We reject the null hypothesis that there is no difference. So that means that the claim, we have strong evidence to suggest that the claim is correct, and that driving while talking on a cell phone does delay your reaction time while driving. Okay, let's go back to the notes. Okay, the next part is, so let me change that also. That should have been a 3, or maybe I just read it wrong from my calculator. I apologize for that. Hopefully you, the last however many minutes, you're not like, what is going on? I apologize. I don't know that I can go back and edit the video, but I will make a note on the video description so that you know that there is a typo. Okay, the next part is produce a 95% confidence interval for the population mean difference in reaction times. And so we'll see if they give us the same answer. So let's go to StatCrunch and get that. By the way, notice that when I did this, I said to find it with summary. I actually have the data here, so I could have also done stat and t-stat one sample with data instead of with summary, since I have the data pulled up, and then I would have chosen the cell phone minus control column, and then my hypothesis is the same, so this will be greater than, and my significance level is 0.05, and compute. And notice that we still get the same things. So our t-stat is 3.67 and our p-value is 0.0011, so we get the same answer. So now let's go to edit this, and everything's already entered here. So but now we're going to do a 95% confidence interval, and so when I click compute on that, it gives me my lower limit and our upper limit. So that is how we find our confidence interval using StatCrunch. If I wanted to do it by hand, then here I give you the tools to do that. So confidence interval is d bar minus the standard error, and d bar plus the standard error gives us the upper limit, where the standard error is our t sub alpha over 2 times the standard deviation over the square root of n. And this t sub alpha over 2 is the one that we already found, the critical value, so the 1.753. And so that's how you will find your standard error, and then if you wanted to do it by hand, but we can use StatCrunch and get to it a lot sooner. But just in case you are like, you don't like StatCrunch or you prefer to do things by hand, then this will be the calculation. You just need to compute the standard error, so it will be the 1.753 times 51.33 over the square root of 16. So find that value and then take your 47.125, subtract that, add it, and then you'll have your confidence interval. So for our case, this is the confidence interval, which notice those are pretty big differences, 19.77 to 74.48. So this actually this means that the average in the differences is between 19.7 milliseconds and 74.48 milliseconds. So that's pretty big, and it's pretty convincing evidence that talking on a cell phone does affect the reaction time, does delay it. And notice again that 0 is not in here. Our hypothesis is that, going back to the null, where is the null? The null hypothesis is that the mean differences is 0. So when I look at the confidence interval, is 0 included in the confidence interval? No. So I can say the confidence interval does not include 0, therefore we reject the null hypothesis. So I kind of wrote it a little bit long here, and you can of course always write this in your own words, make it your own. The confidence interval does not contain 0, the hypothesized parameter. Therefore, we reject the null hypothesis and accept the alternative hypothesis that talking on a cell phone delays reaction time while driving. So somewhere in here, I probably should have had, we have strong evidence to reject the null hypothesis. Interpret what this interval means. I guess I already did that. So maybe this part should have been over here. Okay. So hopefully that helps. So the difference between when you have two dependent samples is that you can find that pairing and then make it, you're essentially turning a 2-sample test into a 1-sample test because you're looking at the difference already. So the differences become your new data values. In this example 2, speed dating, let me just try to get it all in one page. So this is from your textbook data set, and the only reason that I wanted to do something like this is because your textbook doesn't really tell you that this is a match pairs problem. So going back to the data that I gave you, sorry again for scrolling so fast. Notice that I gave you the cell phone time and the control time, and I told you the subjects, right? So this is how I know, oh, subject A did both of them. And when you see data like this in here, how do you know? I guess just by looking at that they're in the same column, that's the pairing. But what I would like to see done here is maybe add another row, sorry, to say that these are the sessions. So speed dating. So let me just read it real quick. Listed below are attribute ratings made by participants in a speed dating session. Each attribute rating is the sum of the ratings of 5 attributes, and then tells you what the attributes are. The listed ratings are from the textbook dataset, speed dating, and you can find it in StatCrunch. Use a 0.05 significance level to test the claim that there is a difference between female attribute ratings and male attribute ratings. So here, right, these are, when it says in a speed dating session, so you have the ratings by females and by males, and so these are the different sessions. I guess what I'm trying to say is that if it were me, I would have added a whole other row up here and say these are the sessions. So you'll have session 1, session 2, session 3, 4, and so on. And then you can see like, oh, in session 1, these are the ratings of males by females. These are the ratings of females by males. So let me look at the difference, right? So it will be 29 minus 36. That will be the difference here. And then compute the difference. But then I know, oh, session 1. So these are my match pairs, right? I'm pairing these with session 1. I'm pairing these with session 2. I'm pairing 23 and 30 with session 8, etc. So just as you read a problem, I'm just kind of thinking on a test, right? If you're going to have different samples, different 2 proportions, 2 means, independent and then dependent. So how are you going to be able to differentiate between dependent and independent? So that's kind of what I'm trying to say here. And so oftentimes this extra column or row, I keep calling it a column, this extra row is helpful in saying like, oh, these are sessions, so these are paired, these are dependent, because those are for the same session, right? My observational units are the sessions, and the variable is the difference in ratings. So that's one of the things that helps. So you can access this data in StackCrunch and do the level of significance. So let's do that super quickly. Now, to access the textbook data sets, you have to do it from your MyLab menu. So when you go to StackCrunch, instead of going to open up StackCrunch, go to view the data sets from your textbook. So you'll go to view the data sets from the textbook, and then you'll find, what was it called? Speed dating. So there it is, speed dating. And so we have lots of data here. So these are the ones that we want: attributes by female, attributes by male. So then we're gonna go to our stat and do the t-stats. So doing the hypothesis test from here, we're gonna go to stat, t-stat, and now notice that we can actually go directly to pair data. So go paired and select your first sample. So we're going to do attributes by female, select the second sample, attributes by male. And we wanted to see that there was a difference, so it didn't say greater or smaller, so just that there is a difference. So then we're going to leave it as equals and not equals, and did ask for a 0.05 level of significance, so we're going to leave that as is for 0.05 and compute. And here is our t-statistic, 0.19, so it's not very high. P-value, wow, the p-value is 0.84, so that is greater than the alpha, 0.05. So then we're gonna fail to reject the null, which means that the null is plausible. So it is possible that there is no difference in the ratings in this speed session. So that's one way you can do it. Notice that going back to the example that we had done with the distracted driving, just to show you, since I just show you how to do the paired sample, we could have also done it here without constructing that extra column. I could have gone to stat, t-stats, because I don't know the population standard deviation, go to paired, paired, and then select column. Cell phone is our treatment, and control is the other one, and we had a right tail test for that one, and 0.05 level of significance, and let's hit compute. And notice that there's our t-statistic, still 3.67, or p-value 0.001. So we can still do it with StackCrunch as well. So sometimes it's like, well, I do the by hand. In case you are struggling with StackCrunch, you still have the tools on how to do it by hand. And so that's why we went through the other one. If you're like, oh, wow, this is way easier, thank you for showing me that, then you're welcome. All right, well, email me if you have any questions.